Hello, everyone. Welcome to another one of our LTS webinars. We're very happy to have you back. Before we begin, I would like to explain real quick the Q&A modality for this session. So at the bottom of your screen, you have a Q&A button, and you're welcome to post your questions there during any time during the presentation. However, due to time constraints, we have only allotted 10 minutes at the end of the presentation for the most interesting questions to be answered. Because of this, the unanswered questions will be answered by our speakers, but this is afterwards, so you will receive the answers by email. And that said, it is my pleasure to introduce Dr. Marek Jersak, who will talk about autonomous drive platforms.
Natasha, yes, thank you. So welcome everybody. Good afternoon to you guys who are in Europe, and good morning to you in the States or other parts of the Western Hemisphere, and good late night to you guys in Asia. So I think we have a pretty big crowd here. So what I'm going to do is now share essentially my webinar here. So my name is Marek Jersak. Thanks for the introduction. So I am responsible at Luxoft Automotive for the autonomous drive practice. I'm going to explain a little bit what that is. So during the next 40 minutes or so, I would like to give you a brief overview of the different areas which are interesting in autonomous drive, give you maybe also a bit of a sense of where we see the challenges, which ones we see well addressed, which ones are of particular interest, what we are doing in this area. It's going to be a little bit themed around the mobility revolution, which is really what we are addressing in Luxoft Automotive. So let's just go right there. And so this is automotive reality in many large metropolitan areas. This is a picture from, happens to be from Los Angeles, place where I used to live for a while. So I know this personally quite well, and I don't enjoy it in particular. Right now, by the way, I'm talking to you from Gothenburg in Sweden. So as this is reality, one of the questions is, well, how could an ideal life look like? And I'm going to borrow a picture here from one of the German car OEMs here from Volkswagen. But of course, this could be any car manufacturer. They have all concepts like that. If you have been to CES, maybe, then you have maybe had an opportunity to see one or the other of those vehicles actually on the road. So the mobility revolution, what we are addressing here at Luxoft is about overall zero emissions, zero accidents, and zero ownership. But today, as we are going to talk about autonomous or about the road to autonomous drive, I'm going to focus primarily on the zero accident piece. So what I would like to cover today, and not necessarily exactly in this order as it is written here, this is the ordering that I provided in the abstract, and it's going to be slightly rearranged, but I would like to give you a sense of the types of architectures that we are looking at in vehicles when we are moving to autonomous, both at the software as well as at the system level, talking about primarily software architectures, including operating systems, middleware, service orientation, and then also, of course, about some of the core software functions that are needed. So sensor-based software, sensor data fusion, all kinds of interesting topics connected to machine learning and AI. Then you will see that in autonomous, the data strategy is actually extremely important. You need a lot of data, to train your systems. So how do you deal with that? And how can you actually automate stuff? So this is going to then lead also to how is software actually developed, or how should software be developed in the future? Where are the shortcomings? How can we work towards continuous integration and continuous delivery? And that will also give us a sense of the kind of ecosystems that we are going to be seeing or already starting to be seeing in this market, and some ideas about software co-development. This is pretty much where I would like to close. So you can see it's a broad range of topics that I'm going to address. I will not be particularly deep on each or any one of them, because otherwise I will simply run out of time. So, but hopefully, depending on your questions, we can follow up on one or the other of those topics, or we can take it offline. So, however, before I go there, just a few words about Luxoft in case you are not aware who we are, and I will promise to keep this little marketing pitch really short. We are an independent global software services provider in multiple verticals, and automotive is our fastest growing, most dynamic vertical. With you know, the number is never quite right, but north of 12 to 13,000 employees all over the world, NASDAQ listed. And the way we are positioning ourselves is really as a core technology and scaling and integration partner with core expertise, but not a product company. And we are really helping our customers to deliver excellence in the projects that they want to achieve. So when we look at Luxoft Automotive, essentially we are divided into three areas of or technical areas of focus. And apart from the autonomous drive, which I have already said I'm heading, there is also our digital cockpit piece, which is essentially concerned with in-vehicle infotainment, head units, cockpit displays, all the really cool looking stuff that you as the driver hopefully will have a lot more time to spend with if you actually don't have to spend so much time driving. So there's obviously a connection. And then there is what we call our connected mobility practice, which is concerned with getting data in and out of the vehicle, and for example, dealing with topics such as telematics or remote diagnostics and these types of things. And there is obviously also a clear indication here. Cybersecurity is a core topic, which is also super important for autonomous, because you don't want your car to be hacked in any way. So having said that, now let's return to the idea of the zero accidents mobility revolution. And to some extent, this picture represents a vision. This is really a fully autonomous vehicle. And the first question that we should be asking ourselves, and I'm going to show you the standard SAE diagram structuring the levels of autonomy. Those who are in the field, you know it, but I'm doing it anyways in case some of you in the audience have not seen it. So essentially, how the SAE is structuring autonomous driving is that starting at the very boring level 0, where there is pretty much no automation, except maybe for something like anti-locking brakes, there are multiple levels of assistant functions. And the simple ones are level 1 and 2, driver assistance and partial automation. And driver assistance essentially means you are still hands-on, yeah. But for example, you would have, for example, adaptive cruise control. So you would, for example, have the car steer the vehicle longitudinal dynamics, so accelerating and braking depending on what's happening in the traffic in front of you. Typically, the type of sensor you would be seeing in a car would be, as a minimum, a radar. So a lot of the cars that you see on the road today, actually quite common now, also in volume cars, have a radar as a sensor, and that allows you, for example, to build an adaptive cruise control function, but it also provides you with the capability to build certain safety functions, for example, emergency braking. Yeah? So emergency braking as a safety function is typically developed independently of the comfort function, which is the cruise control. Okay. Then if you go a level up, partial automation essentially means you could potentially be driving hands-off. Yeah, for example, the car would also take care of steering, and you would have a combination of lane keep, for example, on the highway, together with adaptive cruise control. So you then can essentially, not step on your pedals, not touch the steering wheel, and the car will still be following the car in front of it and stay in lane. So, but you're still in charge. You need to monitor the driving environment, and you cannot ever take your eyes off the road simply because it's just a driving assistance function. So when you go a level up, now we are going into the green zone here, and that is now completely a different animal. So conditional automation essentially allows you to take your eyes off the road in certain conditions. Yeah? So that's why it's called conditional automation. Yeah. So the system is capable enough to actually completely pilot the vehicle under certain driving conditions in a way that you don't have to pay attention to the road, and you can actually, for example, check email. Yeah? So there is one vehicle right now on the road that is level 3. It's the Audi A8, has been recently announced, which has under the condition that you are in a traffic jam situation on the Autobahn or highway, and you are not exceeding a certain maximum speed. I think it's around 50 kilometers per hour, so it's really still kind of crawling. Then you can really detach your eyes from the road, and the car can take care of it. Yeah. Well, and then you go into level 4 and level 5, and this is the future. Yeah? So level 4 and level 5, if you look at the roadmaps of the various OEMs in the market, they're targeting to get there. And there are 2 different ways to get there. So I want to make a distinction here. But they're essentially targeting to get there somewhere ideally in the 2020 to 2021 timeframe. So that's not that far out. Yeah? We are talking, on the order of 4 years. And the interesting thing is that high automation essentially allows you to, go minds off. And the vehicle would, for example, be able to, monitor your condition. And if it feels that something is not right, would, for example, drive to the side of the road, safely park the car, and do an emergency dial, things like that. And going from 3 to 4 is an evolutionary approach, and it's quite interesting to see that OEMs are addressing it, essentially adding levels of sophistication to level 3 systems to get to level 4, step by step. Level 5, full automation. There is a debate, how long will it take to actually get there? And the picture that you saw, this vision from Volkswagen was depicting a level 5 system. And right now, it's probably quite unlikely to see level 5 systems, in an unconditional way very soon. It's everybody's guess how long it will take. But we could potentially see certain types of fully autonomous systems driving under certain particular conditions. Yeah, so there might be certain fully autonomous shuttle services, for example, which are allowed to use certain areas which then are particularly protected. So today I'm going to focus more on going from 2 to 3 to 4 and leave number 5 to everybody's imagination. So looking at going from 3 to 3 to 4, and here I'm just borrowing here actually an image which is this in the particular case comes from Renesas. I like it because it shows the structure of the system quite nicely, and but you can draw your own, and pretty much everybody who's in the field will have some version of this image. So essentially what you have is the sensing and analyzing level, which has all kinds of sensors. And the most important ones are camera and radar, which are widely deployed now in vehicles. LiDAR is quickly catching up. And there is also some augmented information eventually coming from from outside of the vehicle. Yeah? And then there is the fusion and cognitive part in the middle, which essentially makes sense out of all this data, captures what's actually happening around the car, not only in front of the car, but also behind the car, and as you will see, actually also inside the car, because it's actually becoming then quite obvious that if the car does not know what is happening inside, you immediately get a problem when it comes to topics such as handover between a vehicle and driver, one way or the other. So it's also very important to look at what's happening inside the car and essentially cocooning what's going on. So, and then based on this data and diffusion data and the metadata which is derived from there, which essentially describes what's happening, there are those autonomous driving functions. Those are to some extent differentiating, or quite differentiating, depending on what OEM you talk to or what supplier you talk to. They're trying to compete quite heavily there. In the end, there is then the controlling piece. And well, where we are seeing our core activities is essentially in the software development space and function development space. This is where I see the core areas for autonomous drive. And then, of course, in all these software and system integration topics, be it on the algorithm level, but also what are the right architectures, how to deal with data, and so on and so on. And this is both for let's say, higher performance sensor controllers, but also for high performance central compute platforms. And it also reaches out to the overall system architecture. So the EE architecture, the in-vehicle networking part, and you will see a lot of services orientation around that. The other parts are important, but not so much the topic of today's talk. They are essentially the peripheral areas, which I already mentioned, which essentially go outside of the vehicle. And there's also, of course, the motion control interface, which connects the ADAS and autonomous drive functions to the vehicle dynamics functions, which are already in the vehicle, and of course to all the display functions. So there's a couple of core enablers which I'm going to talk about. There's a lot of need for automation in the development, which will go into topics such as agile software development, continuous integration, and there are also all kinds of interesting non-functional topics such as timing analysis, because you really have to keep track of the resources that you are using with your different functions. And before I joined Luxoft, I happened to run my own company, which was focusing on timing analysis. So I have a particular affection to that subject. So I'm going to just mention that a little bit. So that's roughly what I would like to cover. And starting a little bit then from the different sensors and the software development and the functions. So if you start from a big picture of what sensors, those different types of sensors are sensing, and what you would like to do with that, essentially you arrive at a computer vision big picture. And when I say computer vision, I don't necessarily mean camera-based only, but I'm using that as a reference to any of those sensors. So for example, in the lower left corner, you see that there is a fusion happening between an environment model obtained through a camera as well as one obtained from a LiDAR. So, and there is a lot of development happening here in this space. Tons of companies, startups, or more mature companies coming up with ways to smartly recognize and interpret this type of data, and coming up with good algorithms. So there's a lot of also publicly available reference algorithms and platforms on which these types of algorithms can be developed. So if I just show you a few little movies here, this happens to be from the work that we are doing here at Luxoft. You can see, for example, what one of those algorithms might be doing. So you see here an actual road scene. This is the raw data captured by a camera, and then there is essentially you are then on the lower side, you're essentially labeling in different colors the different types of objects that are being recognized. Like, what is the road? What's the sky? What are buildings? What are traffic signs? What are other vehicles? What are pedestrians? And things like that. So this is just one example how those algorithms would work. Yeah? Then, of course, they require a lot of processing power. So we are going to talk a little bit about architectures in a very abstract way. Essentially, you're going to see typically a heterogeneous set of computing hardwares from CPUs, graphical processors, DSPs, custom-made FPGAs doing different pieces of those different algorithms. Okay. So one interesting question is, how good is the data? I told you that data processing is actually a core area that's necessary. Essentially, what we are doing here is we are introducing machine learning, be it either deterministic or based on artificial intelligence, into the system in order to enable it to actually recognize what's happening in front or behind or inside the vehicle. And one of the core tasks, which is very time consuming and quite expensive, is actually to figure out that your algorithm is sufficiently seeing what it is supposed to see in a sufficient amount of conditions. Yeah. So essentially, what you are doing is it's called data labeling. So it's for in this particular case, let's say this is a point cloud coming from a lidar, and so you would be labeling your data. Essentially, you provide some visualization. There may be some additional ways, and you get this picture. This is what your algorithm is doing. And then you need essentially to verify whether what the algorithm is seeing is really what it should be seeing. So you have a lot of humans here, and who are verifying whether what your algorithm is labeling is actually what it should be labeling. So this is a relatively time-consuming process, and it does require a lot of iterations. And as your algorithm or your system is evolving, you have to repeat that quite frequently. So one interesting area to look at is how to improve on that one. And this is just one idea how to do that, to provide a better way of smartly fusing the different sensors that you're using inside the vehicle to come up with an improved accuracy as you are doing your labeling prediction. And there are different ways to actually provide more automation and to verify and validate the labeled data. So this is one of the core areas where there's tons of work. As I mentioned, there is a couple of probably around one startup or so per week entering this space, and there's also something where we are quite active. So I gave you one example with a forward-facing one. Here's another one, how to do this maybe in a slightly different way. For example, to look at driver distraction. So as I mentioned before, one of the core requirements as you're moving from to level 2 to level 3, and then even more to level 4 ADAS systems is to have an understanding what's happening inside the car. So how do you actually label whether a driver is distracted or not? So one idea of, for example, is to do, to actually measure brainwaves. And of course, you don't do that while you're driving. You do that to train the algorithm to recognize, for example, from facial patterns or from movement patterns or something like that, whether the driver is distracted or not. Because if the driver is paying attention or not can actually be measured very nicely using those types of scanning what's happening in your brainwaves. So this is actually a nice way of training such types of algorithms. Yeah. So these were just two examples related to the different sensors that we have in the car, the different ways of using it, of labeling, annotating data, providing some automation in the process. So the next chapter I would like to cover goes more into software as well as system architecture, software architectures that are needed. So yeah, so let's start with typical single SoC based sensor for chip supporting one or more of those sensors. So there's a lot of improvement happening right now here on the market. The sensors are getting better, the resolution is getting better, speed is getting better. Consequently, the SoCs that you need to process the raw data in order to actually extract relevant metadata are also becoming more sophisticated. At the same time, we are compacting them more and more. In order to get the cost down, and there's a lot of interesting work happening in this area related to all the software development part. Typically, when you look at how software is developed, then you have those people who are really good at algorithms, something that you saw in the previous part of the presentation, and those who know how to write automotive grade software. These are not necessarily the same people, or most likely they are not the same people. So there is actually a handover coming from the algorithm developers and then handing it over to the software developers, who are then targeting the actual software platform. So there's lots and lots of use cases here, very interesting for software engineers. So if you are looking for an opportunity to do something highly relevant in embedded software development, this is clearly an area worth taking a look at. Now, I don't want to read all these use cases to you, but it's essentially the whole software development cycle. Yeah. Then the other type of big ECUs, control units that we are seeing, are essentially those high performance integration platforms. So, for example, in the aforementioned Audi A8, there is a big box called the CFAS. So it's German Zentrales Fahrerassistenzsystem. So it's essentially the central driver assistance system, which is implemented there. Yeah, and there you essentially implement all the brains that enable the car, in this particular case, to go all the way up to level 3. And of course, there are many ways to to attach additional sensors there, do some smart fusion here. So there are very interesting and multiple ways how to do that. And here, a lot of both core established, but also new coming suppliers are really racing here to become a core player. It's really interesting to watch what the semiconductor vendors, for example, are doing. With Intel having bought Mobileye, for example, Samsung having bought Harman. So a lot of activity happening here in this space, where large semiconductor vendors are buying big solutions companies who have already made good inroads into the automotive space. Yeah, so let's take a look at the type of software that's running on this. And the first thing you will recognize is that that's actually going to be pretty heterogeneous. Yeah. The days where you could say, well, if it's automotive, you can probably do something in AUTOSAR, and if it's core control, then you would do AUTOSAR, and if it's more cockpit oriented, you might use I don't know, Genevi or some other, maybe Android Auto, any type of lesser automotive hardened. These are kind of gone. So on these high performance platforms, you will have to integrate them. So you are going to see a lot of hypervisor based solutions to let you run different parts of the software in different partitions. But you're also going to see something which is called AUTOSAR Adaptive. So the AUTOSAR adaptive platform is a very interesting development happening right now in the automotive industry. It's driven by a global consortium of automotive OEMs, core suppliers, and also secondary, not secondary, but just the tier ones are the ones bringing the boxes into the car, and then you would have tier twos and services suppliers providing certain components or software pieces or services. So that's something that's happening. And AUTOSAR Adaptive has been released. Initially, there are now 2 releases, one late last year and one early this year. And we are really hoping to get a reference platform running with a bunch of core partners in AUTOSAR, showcasing essentially how you can merge the classical automotive world with this much more visual, not so safety critical, but much more dynamic, agile world. So we as Luxoft, we are AUTOSAR a premium partner. We are contributing quite heavily to this effort. One of the things that we are doing is we are building a demonstrator. So if anybody of you happens to be at Embedded World next week in Nuremberg in Germany, do come by our booth and we can show you how this works. It's actually really fun to watch. And so I don't want to go in all the details here, but essentially what you're seeing here is a containerized Linux-based solution where in multiple containers, you can run an AUTOSAR adaptive stack on one side and a Genevi in-vehicle infotainment software stack for HMI on the other side. The other thing that's really interesting is that here it allows you to actually provide more a Scrum-based agile software development process with continuous integration. So the workflow is very interesting and also quite different to the traditional way of the automotive industry to develop software. Another core aspect of this is that it's moving towards a service-oriented architecture. So there are not that classical automotive fixed communication paths anymore. I don't know if who of you have actually ever worked on a CAN bus, but you define things called communication matrices. It's a very rigid, static setup how things communicate with each other across signals. And that's no longer the case here at that level. It's essentially Siri is messing me up here. Okay, it's essentially a services-oriented way of communicating between different applications. So if we go now a level up and look beyond the single high-performance compute box into the overall network and system architecture of the vehicle, then the service-oriented idea essentially continues. And then essentially you are starting to look at the vehicle and the software on the vehicle as being the different services connected over a services bus. And some services are running on compute units which have a physical link to certain sensors. So you have access to certain sensor data. Others are connected to certain actuators. Others are maybe connected to an antenna interface and provide you access to the rest of the world. And so the service idea continues on the system level. And then when you look at the types of communication backbones that you need for that, it's moving rapidly towards Ethernet-based domain architectures, where, essentially you provide all kinds of services at different levels of granularity as higher levels on some boxes, which can have those different mixes of operating systems and standard software platforms, and all the service infrastructure in between is routed through an in-vehicle automotive-grade Ethernet network. And you will still see, for you who are coming from the automotive industry, very classical AUTOSAR software pieces, but these will be primarily in the areas where all the vehicle dynamics are happening. Where we have the engine control, steering, braking, transmission, and things like that. Certain body electronics. So that's kind of the system level architecture that we are looking at. Now, I mentioned that I'm going to talk quickly about timing analysis. So one of the reasons I want to do that is that when you start looking at integration, and this is done on purpose, looking a little bit chaotic, that's really what it is. I mean, things really start to get really, really complex, and lots of interactions, lots of shared resources that you are sharing in one way or the other, lots of reuse, lots of very complicated sequences from a sensor to an actuator. And so in order to be reasonably confident that this is going to work in all relevant situation, that's where timing analysis becomes a core ingredient. And so here, for example, essentially what is important is to understand, do you actually have enough budget? Do you have a proper schedule? Are you hitting all your deadlines? Can you actually safeguard your end-to-end timing, for example, from sensing that you are, in this particular case, veering out of the lane to making a steering correction. So there's a lot of very, very interesting topics that are timing critical. So timing analysis is really core. There's a bunch of companies that provide very interesting solutions here. I just want to mention what we are doing here right now at Luxoft, and this is also something that if you come to Embedded World, you can take a look at. It's essentially making sure that those non-functional requirements are properly captured. For example, in a DOORS-based or some other tools-based requirement specification, that you properly extract and define test cases for those non-functional properties. And then you continuously track that through your development cycle. Here it's the classic V model, and you do continuously verifying that what you are seeing is actually what you are designing. Okay, so having said that, since I've already shown you a V model as a workflow, now let's look a little bit, get a little bit of the technical layer and look a little bit at collaboration models as they're evolving. And so again, a V model, a very classic way of doing software development in the automotive industry. Yeah? So essentially, it's of course rather simplified. There are loops there, but this is typically how the automotive industry traditionally is showing how software is getting developed. From left top to down to the middle bottom, and then up again on the right. Starting from requirements, doing design, down there implementation, testing, validation, in the end producing the whole thing. So it's a lot of steps and layers and levels, and it's a very sophisticated ecosystem with very sophisticated tool chains, workflows. And there is a big problem with that, because the level of agility, software integration, changes during the lifetime of the vehicle, is not properly supported by this type of software development model. It's too rigid. It does not provide sufficient support for continuous integration. It does not provide sufficient support for co-development with different types of suppliers or technology partners or scaling partners. So there are some ideas how that could be done differently. And obviously, everybody in automotive has heard about Agile and wants to introduce Agile software development, and it is doable for sure. We have to make sure that it is consistent with the rigid software development processes which have been established in the automotive industry for a good reason. So, for example, Automotive Spice is a core one here. And one key thing to understand when you go to Agile in automotive is that while Automotive Spice is mandating what you need to do, so you have to do at each layer, at each level, certain things, and you have to show proof that you are doing it right. The higher the safety level is, the more rigid that proof has to be. But it's not necessarily telling you how to do the software development. This is where Agile comes into the game. So just because you are following Automotive Spice, which tells you what you need to accomplish, does not limit you to actually introduce Agile in order to actually accomplish it. So the how part can actually be done in an Agile way. And this is now becoming quite popular in automotive industry. Looking at RFQs from various OEMs and tier ones that we are typically seeing, we are seeing more and more of those who are essentially mandating an agile software development process, and describing how teams need to be set up, Scrum teams, what kind of agile Scrum-based software development tools need to be used. We can have basically story point based cost calculations. So somebody might actually order 1,000 story points instead of a certain work item or a certain amount of heads for a certain amount of time. So that's actually very, very interesting. And that's a transformation that's happening quite fast right now, and looks really positive. Now, one of the things which such an approach enables is better support for continuous integration, continuous delivery, in particular when you are working in a multi-supplier setup. And that's one of the core process challenges that we are seeing right now in the market, that essentially all the players are trying to be properly on top of this, be it the OEMs, be it system suppliers, but be it also core semiconductor vendors who are building their own software platform and want to enable software integration on that platform. So it's a good way to collaborate, essentially by establishing for a software development with multiple suppliers, common platform, common SDK, common metrics, common dashboard, and have key automation processes. I don't want to read the whole slide here to you, but addressing core topics of software quality, continuous integration, continuous delivery. So this is really a very interesting field. It's clearly developing. There's no silver bullet here right now, and very interesting to see how the ecosystem in the automotive industry here is changing and adjusting to those new ways of doing software. Now, another one that is strongly related and is how you actually do delivery. So I'm using, as Luxoft is a software services provider, I'm using Luxoft here as an example, but I'm sure if you went to a different one, you would probably see a comparable picture. So assuming that a client is not doing all the development themselves, would be on the left side of this slide, and we'll just ignore it. There would be some way for, be it a tier one, be it a different component provider or an OEM, working with suppliers. And there are essentially two classical ways of doing that. One is the very classical staff augmentation model, which is on the left side here in this orange rounded corner box, which essentially just says, look, I don't have enough headcount, or I'm lacking certain skills, and therefore I'm just going to augment my staff with people coming from a services provider. And on the very right side, There is essentially the opposite, which is more of a managed services business model and delivery model, where essentially you just have to write a proper requirement specification, and you receive a statement of work as a response, and then it is the responsibility for the supplier to essentially build that piece of software and then deliver it to you. And in order to go agile, in order to enable these types of continuous integration in a multi-supplier environment, companies are starting heavily to look at different ways to build joint delivery. There are many different ways how to do that. Ideas such as, software houses, project houses, in one location, multiple locations, lots of interesting ideas in this space. Also something that we are very active in helping clients build. I want to show you one example here, which we are doing right now with a German OEM, where essentially we are building a joint software house where part of the team is coming from the OEM and the other part of the team is coming from us. And there could potentially be other parties involved, and they're working under a common roof. It's essentially built around the paradigm of best person for the job. So it's not necessarily defined who would be supplying which role in this type of co-development approach. And it can also change. There's a level of co-management happening. And on that level, we integrate different types of software components, some coming from the OEM, some coming from certain IP providers. For example, there could be a middleware coming from one of the IP providers. Then there are obviously platform softwares, basic software, potentially AutoSAR, potentially some hypervisor, the things that I've already mentioned earlier in the presentation. Yeah. And the idea here is to build together with this OEM the core software, which then gets delivered to a tier one for actually integration and implementation of the production software on the target control unit. Because the OEM is not going to build the control unit themselves, it's still going to be a supplier who is going to do that, and then the supplier delivers the final ECU back to the OEM for the actual manufacturing of the vehicle. Yeah, so that's also a really cool thing, and there's going to be a lot of development from our perspective in this area. Yeah, so that's all I wanted to cover during this webinar, which I'm happy to say puts me pretty well on time and should give us time to answer some questions. So now I actually need to check with the mod. So how do I do this now? I stop sharing and then I can go into QA. Is that how it goes? Okay, let's see. A couple of questions here. Where is Tesla in this leveling? Oh, that's a popular one. So Tesla, and this relates then, I guess, to the initial SAE model of levels. It's essentially level 2 right now. Yeah. So Tesla has all the functions and a lot of sensors, so it can do a lot. But you are still in charge. You are still in control. But of course, Tesla, like all the others, is very heavily moving into higher levels of automation. But the ones that you are buying today or driving today, they are level 2. And well, if you go to Silicon Valley, and there are all kinds of interesting vehicles driving around there, which are prototyping the higher levels. But you will also see those vehicles on the roads in Germany. And I'm not so familiar with the specific setups in Asia, but it's happening in the Asian markets as well. Okay. So what else are we asking here. So, yeah, so a couple of questions here. I'm trying to group this a little bit. Some of them seem to be more around the process. So the adaptation of agile in the automotive industry, a little bit more about the software house, and a lot of the autos are adaptive is called, getting a couple of questions here. What else do I see? Oh yeah, autos are adaptive, a little bit understanding about the supplier space, linking. Okay, so I think I will do one here around autos are adaptive and one around agile, and then I will see what else I have. So autos are adaptive. What kind of middleware services are we using here to connect? It's essentially, well, it's a developing field, which I need to see where I'm in the camera here. And it's, as I said, it's the service-oriented architecture, which is enabling you to connect, in this particular case, as what we used, through a containerization based on a Linux platform, providing the appropriate services, providing a services layer. If it's memory-based communication, then we actually use we can actually use memory-mapped Ethernet. So we are going to see typically Ethernet-based communication, even if things are not necessarily going across a real, well, classical Ethernet cable between different boxes. So that's pretty much how the connection would be happening. So another one around autos are adaptive is more addressing the technology vendor landscape here. So there is a bunch of them. Obviously, the classical AUTOSAR vendors, they are highly interested in that. So if you are familiar with classical software development in automotive, there would be companies such as, for example, Electrobit or Vector Informatic, but there are others. Yeah. So Capit, for example, is doing something. There are also some smaller companies like ArcCore. So these are just some of that I'm just rattling off the top of my head. And they're all very active. I'm sure there is more of them. It's when you look at who is behind it and who is driving this, then similar to the classic AUTOSAR, it's very much initiated by BMW. BMW is really good at launching these types of industry initiatives because they truly believe that those types of platforms should be open, that it's to everybody's benefit. So that's how this goes. Okay. So next one, I said I wanted to talk a little bit about agile. So how long will it take to adapt agile in the auto industry? Well, first of all, it's already there. There are real industry projects, volume, mass production projects requiring now agile. So in the autonomous or ADAS moving to autonomous space, this is happening a lot. It's maybe not fully mature. Sometimes when you look at the requirements, it looks more like agile being a bit of a camouflaged way of saying, I want so and so many people in my team. So if you look at how, for example, the pricing happens in RFQs, it's essentially, well, here's a couple of reference stories. Please do make an estimate how many story points you would require for these reference stories and put a price on it. And it's everybody's own guess how to define the unit of story point. But of course, the buyer on the other side can do a very simple back calculation and figure out what is your hourly rate of the engineers that you're putting on the project. So I would say that when you go to software development, it's becoming more and more agile, at least in these areas. When you go to how RFQs are structured, how pricing is done, you can see that the industry is still getting up to speed, what agile really means. And of course, it does not apply to every area of automotive. So in hardcore, safety critical, vehicle dynamic software development, it's still very much classical automotive software development. Okay. So there's a couple of, oh my God, these are lots of questions. So we will have to take a lot of those offline. I have no chance to answer all these questions. How do you, oh, this is interesting. How do you test software when your hardware is in the car in another country? Well, it depends, I guess, what exactly is meant by that. So let's say you are road testing your sensor fusion or your autonomous drive function doing something. Then typically what you would be doing is you are driving and you are collecting a lot of data. And then in order to manage that data, you are going to need to upload it somewhere because it cannot stay in the car and it will have to go into some pretty big cloud. So some of the numbers that I've heard, how big a cloud actually needs to be, or how much data you're actually going to be processing in order to actually get a level 4 autonomous vehicle on the road is actually pretty impressive. Yeah, so we are talking exascale bytes of data. So that's pretty big. And so you're going to have a massive cloud, and then it really doesn't matter where you are with your vehicle when you road test it. The challenge is more, how do you ensure you have enough bandwidth? Having said that, there are some interesting constraints, which are primarily due to legal reasons. Yeah? So as you know, certain jurisdictions do not allow to, well, export personal data to some other jurisdictions. And if you can imagine that if you are driving with your car on the road and you're filming, you're going to see a lot of interesting things such as license plates or faces. You have pretty smart AI stuff in there, actually able to do face recognition. So that actually puts some interesting limitations on where this data actually is allowed to be stored. Okay. So what else do I have? Maybe just a big one here. Generally, there are a couple of questions here. How big is Luxoft? How are we actually doing this? How are we organizing? And so on and so on. So I actually forgot to say that. And in automotive, we are roughly 2,500 people. And well, we are organized into horizontal technology domains, which are the ones that I mentioned at the very beginning: autonomous drive, digital cockpit, connected mobility. And we are also regionally organized. So we have core experts, customer facing, and we have large teams in various geographies, core automotive software developers who are building the software pieces or testing the different kinds of things that we do. And there's a very tight collaboration between those front-facing and the more back-office oriented people. So this is more or less how we are organized. All right. I probably have like 30 seconds. Maybe just a very quick one here. How are AI and machine learning related? So, wow, that's maybe that's not a short one, but you know, there's deterministic learning, and there's artificial intelligence essentially goes into deep learning, which is per se an agnostic field when it comes to vertical. But it looks like a very, very promising approach for the type of recognition capabilities and decision-making capabilities that you need in automotive.
Awesome.
Okay.
Well, thank you. Yeah, thank you so much, everyone, for joining us. Thank you so much for your presentation. As I said, we will record this presentation. We will send it out to everyone, and the questions that went unanswered will be answered by email. Also, if you could take 5 seconds to answer our quick survey, that would be great, because this allows us to improve our webinars and also allows us to give feedback to our speakers. That said, this was a great webinar. Thank you all so much for attending, and until next time.
Thank you.
Thank you.